Okay, so in this problem, again, we have a cantilever with a distributed load over the first half of the beam, 7 meters, and then at the very end, there's a point load. So the part I want to focus on today is finding the slope. We haven't done one of those. We've done displacements. Let's just focus on the slope one right now. So in all these virtual work problems, the important part is finding the real moment, or the moment due to the real loads. So we look at the real load system here. Looking at the real load system, can I write a single moment equation, or do I have to write multiple ones? I have to write multiple ones. And what I'm going to do, again, too, to save a little time, since it's a cantilever, I am not going to find the reactions. So I'm going to cut the structure here, someplace between 0 and 7, and I'm going to look at the... let me think about this for a second before I say this. I'm reconsidering my options. I don't think I want to do that. I will find the reactions this time. So let's do that. So I know I've got a positive moment at A. That's a bending moment. And a reaction at A. I'll call it RA. I want to find these things. In fact, I don't really need... I need both the reaction and the moment. That's what I want to say. I wasn't saying it correctly. So I'll come here and I'll get a concentrated equivalent of the distributed load. It's rectangular. So the base is 7. The height is 25. So that's, what is that? 175 kilonewtons. And half the distance would be 3.5 meters. So if I come over here and I sum moments at A, using right-hand rule, solving for equilibrium, according to that, this moment is a negative moment. About A, my concentrated equivalent load also is negative, so the force would be 175 and a distance of 3.5 meters. And then the 75 kilonewton force way out here on the end also creates negative moment. And that has a moment arm of 14. So somebody can tell me what the moment is. I believe it's going to be negative. I don't know what that is. Somebody calculate that for me real quick. 1663. And that will be kilonewton meters. And it's negative. That makes sense. Anybody else get that, by the way? Is that confirmed? I'll let you work on that. I'll go ahead and write the next equation. You got that? Great. So we'll go ahead and now sum forces in the vertical direction, the y direction. I'll assume up is positive. So I have my reaction at A is up, and my other two forces are down. My concentrated equivalent is down, 175 kilonewtons, and the applied load here is also down 75. So it looks like the reaction at A is 250. So we probably have just enough time to do the real moment. So we'll look at the real system. So I'll look at the real moment. From our previous discussion, we know that we're going to have a moment equation that's good from 0 to 7, and then a second one from 7 to 14. So the first one will be valid from 0 to 7. So if I cut that here, I've got this really messy bit on the right, or I've got a little more nicer bit to the left. I'll go to the left this time. So at some distance x, internally at that cut, I have my positive moment. I have the reaction moment here, which I solved for as 1663, and that's kilonewton meters. And I have the vertical reaction, which I solved for, which is 250 kilonewtons. And then I have the distributed load. I didn't really leave myself much room to draw this. Sorry about that. The height is 25 times x, so this will have a force of 25x, and of course the distance from the cut is x over 2. So when I sum moments at the cut to find the internal moment for this, what do I have? Well, with right-hand rule, I have my internal moment. That's positive. About the cut, the concentrated equivalent force creates a positive moment, and that would be 25x times a moment arm of x over 2. The reaction creates negative moment. That would be negative 250. The distance is x. At the very end, I have this applied moment, my reaction moment, which is positive. So if I solve for the moment now, I get this expression. So what do I get? It looks like I get minus 25x squared over 2 plus 250x minus 1663, and that would have units of kilonewton meters. And the only thing I can really check there is I know that my moment at x equal to 0 is the reaction. So that would be a negative bending moment of 1663 kilonewton meters. And when you put in x equals 0 here, you do get negative. So that's, I can't check it at the free end because this is only good from 0 to 7. So let's do it one more time. Now this will be good from 7 to 14. And I think this free body will be a little easier to draw. So there's the cut. I'm cutting it here looking to the right. So I'm making a cut here looking to the right side. So the distance up to the cut would be x. The right-hand side segment of that would be the total length, which is 14 minus x. And then at the free end, I have this load of 75 kilonewtons. And then internally, there's my positive moment. So we'll finish this up for today. We'll sum moments at this cut. Make sure it's in equilibrium. So internally, this moment is negative with my sign convention. And about the cut, the 75 also creates negative. So the force is 75. The distance is 14 minus x. So it looks like my moment as a function of x will be minus 75, 14 minus x. And that has the same units as before, kilonewton meters. Well, I can check this too. I know the moment at x equal to the endpoint 14 should be 0. And when I put in x equal 14, I do get 0. So I checked my two endpoints. You could also check them at b. You could put in 7 into this equation and 7 into this equation. You should get the same result. So that's all we have time for today, but I'll pick up with this on Thursday, and the video will have to come in 2 parts. All right, see you guys Thursday.